Hello, my name is Dan Low. In this video, I'm going to talk about programs are countable, but languages are not countable, actually, are uncountable. Okay, so why? Um, so that's the first. Take a look at the countable. So what is countable? So countable means that you can count items one, two, three, four, for a set. Okay, so for example, the natural integers. Okay, all the natural integers, 1, 2, 3, 4, 5, 6 are countable. You can count 1, 2, 3, 4 all the way up, so you call countable. And real numbers, however, are not countable. So let's say we you can count the real numbers. Let's say you count real number R1, R2, R3, R4, and up. Okay, let's say if you could. Then how about R1 plus R2 divided by 2? Somewhere, some numbers in between R1 and R2 in the middle. Is it a real number? Yes, but you you def it out. Okay, you don't count it. So that means the real numbers are not countable. Okay, so a countable set allows to count its elements 1, 2, 3, 4, and up, and nobody got left out. Okay, so a program is a binary string. You can look at the program, view a program, um, say written, in whatever language, like a C language, Java language, Python, Scala, VBA, Fortran, assembly, whatever you name it. Okay, so a program, it's stored in a computer by I would say long binary string. If you look at the memory, okay, to store the program is a long binary string. Okay, like this 01000111 whatever. Okay, in computer memory. So a program can be viewed as a long binary string. So the set P, let's say you put all the possible programs together in a set. We call it P. And then this set includes both the valid program and invalid program. Okay, and it's actually the set of all binary strings. So the set of binary strings. Now the set P is countable. Why? Since the programs we can collect them, in a set of binary strings, so we can convert a binary string to its corresponding decimal number. Okay, and then we can get to count pi, for example, for the program whose decimal value is I. Okay, so therefore, the programs are countable. You count pi, the ith program. Okay, whether it's valid or invalid, it's a program, it's a binary string. So you can look at it that way. Now, let's talk about what is a language. Okay, a language is a set of strings over an alphabet set that is finite. Okay, so for example, English is a language, which is a set of words over the alphabet A to Z. Okay, and consider the alphabet, to make things simple. First, the alphabet just 0 and 1. We have the two symbols, 0 and 1. So all possible strings, including 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and up. So this this set of possible strings um, will be the set of strings we consider for language. So, and this set of strings is actually, this, in computer science, we call this set is sigma, and all possible strings is sigma star. Okay, and we counted the ith string whose value is I. So sigma star is actually countable. You can count the ith string, okay, whose value is I. You can count, okay, just like all the programs. we considered earlier. Okay, it's countable. And a language is a subset of those strings. Those strings, a subset of the set of all the strings, basically. Okay, all the binary strings. Let me put it that way. Okay, so language is a subset of it. So for example, you can have a subset 0, 1. Okay, that's a language. Another language 1, 1, 0, 1, 0, 1, and so forth. Or possible subset from this, all possible strings, binary strings, by the way. Okay, and we can view the language. There's language 1, language 2, like this. Okay, like they are corresponding decimal value for the binary 0 and decimal 0, binary 1 decimal 1, and then this is also 1, and binary 110. Okay, not 110, sorry, 10, and then the decimal is 2. Okay, and the binary 101, the decimal is 5. Okay, so you can think of each language is a set of natural numbers, or including 0. Okay, any combination of natural numbers. So you can view a language like that. Okay, now why languages are uncountable? Okay, so all possible languages are all possible subsets of all possible strings we've defined earlier. So let's assume, we're gonna prove by contradiction. Okay, let's assume we can count the language or in the set. Okay, so assume we can count each language. Let's say the language 1, language 2, and so forth. Okay, and now we can create a language L. Okay, based on the counting L1, L2, L3. Okay, that contain the strings I not in Li. Remember the L1 contain some natural numbers. L2 also contains some natural numbers. Okay, so you look at that way. Okay, so the string I, whose value in decimal value is I. Okay, if it's not in Li, okay, then we get that string into L. Okay, so L contains the string I if it's not in the Li. All right, so if you state it formally, L is actually a set of strings, and each of the strings is the I string, and where the I is not in Li for all I is equal to 1, 2, 3, 4 all the way up. Okay, so obviously L is different from each Li. Okay, because for example the L2, if L2 does not contain string 2, then L contains string 2, so that's different. Okay, so L is obviously different from L2 or in the string I, because the string I is in either L2 or L, so they are different. Okay, and the similar argument can be applied to all the language L1 all the way up. Okay, and therefore L it must be different from all of them. Okay, but now L is a subset, right? It's a subset of the all possible strings, so it is a language, but you don't count it, so that causes problem. So however L is not counted, therefore languages are countable. That concludes this. I hope you enjoy. Have a good day. Bye.